Welcome to the unit 8 on the module of control. So, what we are discussing as of now in this module, that how basically we can execute the controls if the methodology is a microprogram control. So, in the last unit basically we have seen the very basic idea of a microprogram control unit, that given a mainly we have discussed only the fetch part of the instruction. In fetch part of the instruction we have seen that what are the corresponding signals and how we write it in a microprogram control memory and how we go through them. Then we have discussed how basically we can optimize it, because in case of a microprogram control memory we just give the signals which has to be made zeros and 1 and we write it into the memory, and then what we do basically one after another we keep on fetching them and we are putting those output of the memory are directly given as fed to the ports. But then we have seen that there are a lot of zeros in this memory, then we have seen how to optimize them using a vertical and hybrid microprogram. But in this basically what we will try to do, we will be mainly focusing on optimization of microprogram control unit in more depth and by taking more specific examples, and also another focus will be we will try to see the execution of a full instruction, because in the last unit we just saw about only the fetch part of it. That is, this unit is basically an extension of the previous unit. In fact, the microprogram is a slightly larger topic, so we have dedicated 2 units for that. So, this is the part we are going to cover, and then as the pedagogical method, so we will see what is the summary of this unit. So, basically a full program, which is one of the main emphasis, how to see a full program which is written, or the idea we will get that how one or after the macro instructions are executed in terms of a micro instructions when it is a microprogram concept. So, a full program is written in terms of machine instruction, that is the macro program, how it is executed. For each machine instruction, when it is in the decoding cycle, based on the opcode, the corresponding microprogram is loaded into the memory. For first phase they have is very simple, that is the fetch. So, already we have seen that for each fetch the corresponding 3 micro instructions are executed. After that basically it waits. That means what? So, whenever a new instruction has to be executed, the microprogram PC is pointed to the instruction which corresponds to basically your fetch. So, if you think about this is your microprogram memory, maybe these 3 are dedicated for fetch. So, whenever a new instruction is macro instruction is to be executed, the microprogram counter will point to this. After it has done, it will come to the end of the fetch part. Then what happens? Then the instruction register actually decode what the exact instruction is. If it is add, if it is store, if it is load, accordingly the MPC will be pointed to different part. Maybe this part of the memory corresponds to add, so it will jump over here. Maybe it is for subtract or multiply. So, if it is multiply, so it will from here it will actually jump to here. That means based on the instruction register, based on the macro program or the macro instruction being executed, it will actually load the microprogram MPC corresponding to the microprogram for that instruction, like this may be for add, this may be for multiply. Then it starts actually the real execution of this instruction in terms of its microprogram. So, this is one thing we are going to see for some template instructions. The microprogram counter fetches each micro instruction in sequence and they generate the required signal, or if required jumps will also be there. So, but basically it goes to this point and to the add or respective instruction to be executed corresponding to the IR instruction register which is being decoded, that is the real execution starts, and it will keep on doing it till it gets ends. So, once the present microprogram is complete, the next microprogram is loaded based on the new instruction. So, once this add has been done, then again automatically it finishes, then automatically the microprogram will start pointing to this part which is actually again fetch. So, it will actually fetch the new instruction. So, now the MPC, this program will be executed. So, from the MPC will be pointing out to this microprogram memory which corresponds to fetch. So, automatically again new macro instruction will fetch and the procedure will go. So, there are basically 3 steps. When a new macro instruction has to be executed, it will first load the MPC, correspond to the microprogram memory address, microprogram control memory address which correspond to fetch. 3 instructions will be executed. Then again the MPC will wait to get a new value. So, where the value will come from? The instruction register by that time has decoded the macro instruction, and corresponding to each macro instruction like add, multiply, store, or different address formats, it will actually point to the corresponding microprogram in the memory. Then it will keep on executing that, and once it is done, the whole instruction is completed and a new macro instruction has to be executed. Then again the fetch part starts and he keep on going in. So that is actually what is the idea of a total program execution in terms of a microprogram control. So now how you can do it? A very simple solution. For each machine instruction you write a microprogram. For fetch it is 1, because and then for add you write 1, for load you write 1, for subtract you write 1, and they can take a very huge microprogram memory. From the fetch part will be there, after that there will be add, then again for the next instruction there will be again fetch, and again the corresponding real execution microprogram will be there, and you keep on doing it. It will be a huge code with lot of redundancies. So what is the solution? That basically, because there are so many different type of addressing modes, etc. So, and if you write different microcodes for each addressing modes, each type of instruction type, so it will be a huge memory, but you can do it, it will solve the problem. Depending on the IR decoding, you can directly go to that instruction and execute it. But that is actually going to a very unoptimized solution. So what we do, basically we try to keep something in common. For example, the fetch part is common to all. So there will be only a 3 bits or 3 word memory for fetch. And then for example, if we have subtract and say add, 2 instructions are there. So only difference will be basically is subtract will make the ALU to sub, subtraction will require the signal which corresponds to the ALU, sub should be made 1, and in case of add the control unit control input to the ALU which is corresponds to add will be 1. Other than that the whole program will be similar. So therefore basically we can write a single microprogram for add and sub with just a branching instruction, that if we find out the instruction decoder is saying for the sub, then a slight change will go to one part, and if it is add you just go to one part and the other part can be common. So that one we will actually save in the microprogram memory size. So that is the common part of the micro routines can be shared, which will reduce, but in that case we will require a lot of branching part, but that is however is okay. That is whatever is common you put together, and whenever you have to go to some other part of the other instruction which is uncommon between them, as I told you in this case only one word will be different, in which case sub will be equal to 1, and in which case the add will be equal to 1, because they need to configure the ALU in different mode. Only that instruction will be different. So you can easily write a branching program which will do accordingly. So basically the microprograms are written in a branching fashion. So that is one of the key idea of this unit which we will be starting to look at basically. We will take a full instruction and see how it executes, and also at the same time we are also going to study how basically this branching should happen. And at the same time we will also try to see that basically we will take one practical example of a instruction, and we will also see how we can practically optimize the instructions based on clustering, because in the last unit we have just given an idea of clustering, but here we are going to take a much more elaborate look at how the optimization can do. So therefore there are the 2 basic things we are going to focus here. So what is the objective of this unit? Because as we are following a pedagogical approach, so for each unit we actually define the objectives, and in the end we try to see whether the objectives have been met. So what is the objective? The comprehension objective, explain about the branch control mechanism in microprogram. That is very important. This should be able to do it, because without branching it will be a very unoptimized solution. And in fact if there are branch instructions, obviously microprogram has to follow a branching part, and not only because of the inherent program should have branching, there should be a branching in the micro instructions, also because I told you in microprogram lot of parts of different microprograms corresponding to different macro instructions will be similar, so you have to branch in between them to optimize the memory size. Then estimate the size of control unit to implement the control store to implement the control unit. That is, you have to estimate the size of the control, you have to estimate the size of the address part, also you have to find out the how many signals are there. So all this based on a certain memory architecture of a single bus or multipass, you should be able to, mainly we will be concentrating here on a single bus architecture, you should be able to estimate what are the different bits required to store each part of the control memory. That corresponds to the control signal generation, then the condition check, as always the branching address check. And as an application objective, demonstrate the impact on performance of control word depending on the format of the control word. That means performance based on the format of control. So example, if you have a very compressed format, so the control unit will take no time. If it is a very flat like a horizontal format, then it will be very fast. So you will be able to demonstrate the efficiency based on the format of the control unit, format of the control word basically. That means whether it is a full horizontal, vertical or hybrid. So, these are the basic 3 objectives. So, let us start with the unit. So, basically what happens, as we were discussing, for each instruction of the CPU there is a corresponding microprogram for generating the control signals. For each macro instruction there will be a micro instruction, there will be a microprogram. Each microprogram is sequence of micro instructions and it is nothing but zeros and ones which is in a memory, as you have already seen. Each position of the control word specifies a particular signal and is placed in the memory. So, it can be 0 and 1 and you can directly take the memory word out, control memory word out and give it to the respective ports. So, that basically they are actually called the control memory and we generally call it the microprogram control memory. Since this machine instruction is executed corresponding to a microprogram, it follows the starting address of the micro routine as specified as a function of the contents of IR. This is very important. As I was saying that there are different macro instructions. What the macro instruction should do will be decoded by the instruction decoder taking the values from IR. So, based on the IR value, the instruction decoder value, you should be able to point out to a location in the main in the microprogram control memory which corresponds to the microprogram for that macro instruction. And as I told you, generally we are trying to have we do not try to keep this control memory very long by giving separate microprograms for each macro instruction. Rather we try to write a common program and for each of taking a set of macro instructions by trying to keep the common part similar, and if there is wherever there are diversions you can put jumps. So, that is how basically it works. And in fact, as I told you, branch to incorporate branching, here also you will require to check the contents of the code, control status flag, etc. So, that already we have seen in the last unit, that basically if the jump instruction is there, you have to check for some control fields as well as the control can be from the status as well as from the some signals actually which is coming from the IO devices. So, that is very similar to a macro program branch, but actually here branching is 2, that is one thing you have to emphasize. One is a normal branch. The normal branch means basically what corresponds to the macro program. So, if the macro program says that you have to do a branch based on a condition, the micro program will branch correspondingly. Another is micro program inherent branch, that is inherent branching. So, why this inherent branching is there? Basically, as I told you, because if there is add instruction and sub instruction, we do not require 2 different micro programs for that. We will have same, but depending on the if it is a add or a subtract, we actually branch to a part which is the only uncommon part and then again come back and follow the common part of it. So, there is some inherent nature of optimization of the microprogram, so that you require inherent jumping, so that we can have a common program and jumps are done only when the instructions are the different part we can do. So, we can have a similar same micro instruction for both add, subtract, load, maybe whatever are the common instructions. So, therefore, we require many branches in a microprogram execution compared to a macro program. So, basically a full program written in terms of machine instruction basically executes as follows. For each machine instruction, that is the macro instruction, when it is in the decoding phase, as I already told you, the fetch is over. First there is a fetch phase. The opcode actually corresponds to the microprogram. The opcode corresponding to the microprogram is loaded into the control memory. Basically, that the idea is that in this case you can just think in this manner, that whenever a macro instruction is there, has come to this come for execution, immediately you execute the micro instruction for fetch. After that, basically there is a decoding. So, once the decoding is done, basically that is the decoding cycle. So, when the decoding is done, the corresponding MPC points to the memory of the microprogram which corresponds to that particular instruction. So, if there are, as I told you, if there are multiple instructions like add, sub, multiply, which will be similarly we have made a single code to optimize space, then for any of these instructions you start pointing to the start point of that corresponding instruction. Now, whether it is a add or subtraction or multiply, at one point of time it will diverge out and again come back. For example, as I told you, if you have add R1M and say add subtract R1M. So, only one point, that is the control of the ALU will be different. So, only that part it will diverge and again come back, because after doing the computation again you have to write back the value of, because many parts will be common like loading the value of M from the memory, then again after doing the computation the values has to be written to R, and those parts of the micro instructions will be common. So, that part will be common and only the jump will be based on the signals made to the ALU. We will take an example which will make the things clear, but just we are giving the brief theory here. And then the microprogram counter fetches each micro instruction and they execute in sequence, or jumps to the required location. So, when there are jumps, there will be 2 jumps, when it is an inherent jump because of the macro program, and when because of this optimization of the memory space, the microprogram is common to many instructions taken together. So, you have to jump accordingly, and then the IR actually in the instruction register tells where to jump. So, how it exactly implements we will see. So, once the microprogram is controlled, the next microprogram is loaded based on the new instruction, that is very important. So, when add has been done, so now add is complete, then the MPC will start pointing to again the fetch part of it, that is it corresponds to the new instruction or the new macro program, macro instruction. Okay. So, this is just again very quickly let us look at, now we are going to take a more elaborate depth with more clear examples that how optimization is done on the signals by encoding. So, last unit we have already discussed that encoding is very important. So, if you do not encode, basically what is going to happen, if there are n control signals in a CPU, the length of each control word of the memory will be n. Very simple, there is a horizontal microprogram, everything is parallel. This is actually a horizontal microprogram and it is going to be very fast, but the memory is unoptimized. To do this, we have seen that in the last unit that we have to optimize by encoding the signals, which is actually called the vertical micro instruction. So, if you just go for a very flat compression, that is from 2 to the power n, you just compress it to n or from n to log n and using a n to 2 to the power n decoder, then actually full compression is there and it is actually called a full vertical microprogram. But in this case only 1 bit signal can be made a 1. So, if simultaneously 3 or 4 points need to be a 1, you require 4 cycles for that. But we have seen that is not a very good way of solving the problem, because it makes the memory very small, but it will take very long time to solve the problem. So, what we basically do is that we go for basically something called a hybrid approach. In hybrid we make clustering, and for each clustering we will try to put signals in one cluster which need not be one simultaneously. So, that is one idea of actually called a hybrid microprogram. So, that approach actually we are going to see with a more elaborate example, because in the last unit we have discussed the basics. So, this slide tells about the horizontal microprogram, that it is one extreme and it is basically it is longer, and in the vertical microprogram it is highly compressed. So, it is the other extreme. So, whatever I was discussing is basically written in this slide. You can go through this, the theory part of it. Now, this is very important. So, we are taking a single bus architecture. Now, we will mainly focusing on example, because theory mainly we have covered in the last unit. So, if you look at it, this is a single bus architecture. So, in this we are will try to find out basically how we can optimize the vertical and horizontal microprogram taken together. That is your basically a hybrid kind of architecture we will consider for the microprogram memory, and we will be taking a single bus architecture to use it. So, what is an assumption here? We assume that here there are 4 temporary registers R0, R1, R2, R3. So, the number of signals are 0, 1, in, out, in, out, in, out. So, 4 registers are there and in and outs are there. So, just remember how many signals are there? 8 signals are there. Then there are 3 system registers which a user cannot use, and they are used for some system storage. So, 1, 2, 3. So, that is temp, destination and source. Some registers are there. So, how many registers total? 1, 2, 3, 4, 5, 6, 7, and for each register you have an input and output port. So, it is 7 into 2, 14 signals are there, just keep it in mind. Then we have an instruction register. So, instruction register always takes the input. So, IR in is there, that is 1. So, 14 plus 1, 15 signals are there. Program counter in and out 14, 15, 16, 17. Memory address register in, so it is 18, 14, 15, 16, 17, 18. Memory data register in and out 18 plus 2 9, 18 plus 2 20. Then this is your CPU. So, you can say Y in, then basically your functions, that will be again some control lines for the functions, and then basically Z in and Z out. So, let us count how many input and output ports are there. So, 1, 2, there are 4 user registers, 3 system registers, 7 into 2, 14. Then 15, 16, 17, 18, 19, 20, 21, 22, 23, I have missed something, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, sorry 10 over here, and 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 20, actually there are 24 signals will be there, you just count, I may have missed something. So, there are 24 input output ports you will find out, 14, there are 14 over here, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, yeah. So, just count over here. So, these input output ports if you look at, you will find out that there are 24 input output ports, the signals I will show you. Along with that, that means there are 24 ports to be controlled which corresponds to input or output of any register like MDR, MAR, R0 to R4, source destination, Y, Z, Z in, Z out. So, if you count there are 24 signals which correspond to those values, and therefore also there should be some signals which will tell you that whether it should be add, subtract, multiply. So, those signals will also be there. So, now we will try to see based on this architecture how we can optimize based on clustering. So, assigning individual bits to each signal leads to a long micro instruction, because here we have counted that there are 24 input output ports, then for some signals will be there to control the ALU, that also you have to add. Along with that you have to have some signals like this select, add, select, W for read, that is memory read or write, there should be one signal, then wait for WFMC will be one signal. So, there are several other signals and the count will be quite large. So, let us see what are the counts. So, we will see the count in the next slide, but if you take all the counts and put it in a flat architecture, the size will be very high. Already we have discussed so many times, which will be a horizontal microprogram. So, this will obviously lead to lower bit space utilization, which is the case in horizontal microprogram. So, as I told you, we are assuming that there are 4 user purpose registers. There are 3 source registers, there are 4 user purpose registers, there are 3 SIP central registers, and basically as we have counted, corresponding like a memory address register, memory data register, Z, Y. So, there are 24 getting signals as we have counted in that figure. Along with that basically read, write, clear, set, carry in, some signals WFMC, N. So, these signals can be more, but in this example we are assuming that these many other extra signals are there like read, write from the memory, clear means clearing some value of Y in a register, set, carry in, that is the carry in of the ALU, wait for the memory, and end. So, this also actually correspond to 1, 2, 3, 4, 5, 6. There are another 6 signals are there. 24 signals were there for the input output of the registers, which you have counted in the bus architecture. And let us assume that there are 16 different operations which the ALU can do, like add, subtract, and, or, compare, so many other signals are there. Let us assume that 16 different functionalities are possible. So, there will be 16 different lines. Just like again I am going back, so there will be 16 lines over here, and if you take all these control lines for the registers, there will be another 24, and they have assumed that 6 more control lines are there which corresponds to read, write, carry in. Okay. So, they are corresponding to read, write, carry in, WFMC. So, another 6 more signals are required for some other interfacing. So, together there will be 46 signals required if you want to do it in parallel. So, the memory word size will be how much? It will be 46 bits in a horizontal microprogram. So, therefore, it says that there is 46 different signals are there, and therefore, basically 46 will be the length of the microprogram array. And it has been found theoretically that only 10 to 15% of the memory positions are 1. So, if you have such a big array whose size is 46 and it will be long depending on how many micro instructions are there, and only 15% is actually filled with ones, it is a huge waste of memory. That is why we go for either vertical microprogram, or if micro multiprogram is very slower, because in this case it will be log to 46. So, I think around 6 bits will 2 to the power 5 is 32. So, 2 to the power 6 is 64. So, 6 bits will actually solve the problem for you. So, if I go for a full encoding architecture, so it will be 6 bits which will encode, and then you can use 6 is to the 64 bit architecture using a decoder, and the job will be done. But in that case it will be very, very slow, because simultaneously only 1 bit can be made 1. So, in fact, it is not a very good idea to solve the problem. So, we can go for a clustering approach which is called the hybrid microprogram. So, that is what actually we are going to study. Before that, how to make a cluster and what will be the idea for that, that we have to thoroughly think, and we have to make the cluster. So, if you go for a flat architecture, that is each bit can be in cluster, the horizontal microprogram one extreme, and if I go for full encoding, that is 6 bits will be required to encode all the 46 bits, and it will be a very compressed architecture, but at a point only 1 bit can be a 1, which is actually written over here. So, it will be very, very slow. So now let us try to think how we can make clusters. Say for the time being, just assume that there is F1, F2, F3, F4, F5, some 10 clusters they have thought about. So I will try to see. So think some basically on some thumb rules we make the clusters. For example, PC out, MDR out, this circle if you see, this cluster, all the outputs of the registers I put in one cluster. This is because it is a single bus architecture. So simultaneously R1 out, R2 out, R3 out, source out cannot be done. It leads to a conflict. That is, if you look at this, figure, so if you are single bus architecture, so all these registers, all these 24 story I was talking about, only one bit can be out at a time. Other single bus there will be a problem. So it is very wise that you put all the basically out signals in one cluster. That means idea is that in one cluster only one bit can be made of one at a time. So there is no problem, 1, 2, 3, 4, all the outs you actually put in one cluster. Then your job is done, because simultaneously only one bit can be one, and that is what is required, because simultaneously R2 out and R3 out cannot be made one. So actually how many such instructions are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So if you calculate, there will be 1, 2, 3, 4, 5, 6 or some 4, 10 or 11 out signals for the registers. So how many bits are required? You will require 4 bits to solve the problem. So you require a 4:16 decoder for this. And in this case, I mean because the full decoder will not be used, because you do not have 16 such signals. So you can just say 0, 0, 0 for no transfer, that means nothing will happen, and all the other bits are actually don't care. In all the cases there will be no outputs. But if it is 0, 0, 1, PC out will be 1, if it is 0, 0, 0, 1, then MDR out will be 1, and your job is done. Then another important cluster is actually, I will put, because I told you there are actually 16 different functions of the ALU. So I can club all the controls in one decoder, in one cluster, because simultaneously I cannot have add and sub. Simultaneously only one can be high. So I actually cluster everything, make a one cluster. Your job is done. So this is two very key rules, that all the outputs basically you put in one cluster, all the CPU functionalities you put in one cluster, because simultaneously two cannot be one and simultaneously ALU cannot do operations. But this logic only holds if it is a single bit architecture, bus architecture. If it is a multiple bus architecture, then 2 bits also can be simultaneously 1, and then again you have to break it up in the cluster. So in this discussion we are keeping this thing simple. So in a single bus architecture, this is one of the very good way of doing it. Now read. So read can be multiple, because it can happen that there will be only one output, but simultaneously 2 or 3 guys can take the inputs together. So based on that you can make some architecture or clustering. In this case they have put PC in, IR in, Z in, all the registers in one cluster, MDR, MIR in one cluster, Y source in one cluster. So this clustering they have made based on some philosophy. That is, they have thought that, like they have thought that PC in and IR in, they are keeping it in basically one cluster. That means they have found out that both reading the value of PC, that is loading the value of loading the value, updated value to PC, and loading the IR generally does not happen in one cycle. So they have put it in one, and they have also thought that in the same cycle register, when you are updating the PC, therefore or a instruction is loaded into the instruction register, R0, R1, R2 and R3 basically do not read at the same cycle, because when a PC is updated, generally the temporary registers do not read the values. For example, when you are dumping the value of Z, that is the output of the ALU goes to Z, and then in the next cycle only it goes to the different registers. So when you are updating the output of the ALU in Z, at that cycle basically the registers do not get updated, because first the output of the ALU goes to Z, and then in the next cycle it actually goes to the registers. So they have kept all the R ins basically with Z ins. But that is why they have made one cluster, and they have found out how many instructions are there, 1, 2, 3 signals are there, 1, 2, 3, 4, 5, 6, 7. So 7, of course 3 bits are required, and 1 may be a don't care case. But they have thought somehow that basically it may happen that some PC output basically generally goes to memory address register in, so that they have put in over here. So PC out generally goes to memory address register. But they also might have thought that sometimes you may read the value of program counter in terms temporary registers for some storing the value or studying the current instruction, or you can also think that means basically register value out can go to R in, and also it may go to basically memory address register in if it is an indirect addressing kind of a mode. So it may happen that the output of basically one register can go to multiple registers, or the PC output can go to a temporary register as well as it can go to the memory address register. So in that philosophy, they have decided to put basically the user registers over here and the memory address register or the memory data register or temp in another cluster. That means basically simultaneously one register can be made 1 and one register can be made 1 here, and even one register can be made 1 here, the input. So simultaneously some output can be fed to one register over here, one register over here and one register over here. That is where you require simultaneous input is possible, more likely you that way divide the cluster. If you would have thought that okay, just like your output, I just think that only one register can be input at a time. So we could have put all these in another cluster and then you could have saved in space. But here they are assumed that I am making the cluster based on simultaneous inputs which is possible to the registers. So based on that philosophy, they have divided the signals into different clusters corresponding to that single bus architecture. And there were some other control signals, as I told you, that there is something called read. Again I am putting the read in a single cluster because the memory can be read or write at one go, and similarly like this is the carry in, you are putting in one cluster because carry can be either 0 and 1 and so forth. That is wait, because wait can be simultaneously 1 with anything else, so you can put it 1 and then end and continue on the two signals. So these are some of the other control signals for the memory and wait for memory cycle, etc. Because if I want to put this one over here, this is not a good idea because generally we give read and write and simultaneously also we require to wait for the memory signal to be ready. So we put this read write in one cluster and WFMC in one cluster. So this example actually gives you a broad, in the last unit we actually gave you the philosophical idea that why clustering, how it can be made a clusters and why you require to put everything in one cluster. If you put, it will become a full vertical microprogram, very slow. If you make everything single cluster, it will be a horizontal microprogram, very fast but very inefficient. Here we have given a single bus architecture, a real example with each bits, signals and registers and ALU. So one pure example or a concrete example we have taken for a single bus architecture, and then we have made a cluster for all the signals based on the philosophy of clustering. So this one actually examples the theory we discussed in the previous unit in a more practical example. Okay, so basically, so whatever I have discussed is written in this slide. You can go through here. Basically, why I put read write in one point, why the 16 ALU functions are put in one cluster. So whatever I was telling, I have kept it in this slide so that you can read it offline. So now what is the gain? So if you see the gain, so how many bits are required? 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So 21 bits are required to solve the problem vis-a-vis the 46 bits required in the extreme flat case. And if you look at it, how the way we have clustered it, very few cases there will be contention. That very few cases you can have both R2 and R2 in together. In that case you have to split it. But mostly basically you will have as similar performance as a fully horizontal architecture, and still you have saved a lot in the space of the memory. So basically if you also, that is what I have said here, all the philosophy is extended, and please go through this slide to find out what is the basically I have told about this grouping and what are the advantages. So these two slides, this slide and this slide, tells what the advantages and what are the gains and what are the drawbacks of the basic clustering philosophy we have taught for this example. You can go through this slide offline and get the values. So in fact they have find out basically, so instead of 40 signals we have basically now F10 values, number of word is 21, so huge save in space, but of course some additional things are required. We require some decoders over here also. Some decoders are also required, like for some groups basically we require 4:16 decoder, for some group 3:8 decoder, and for some case 2:4 decoders. So not only you have to find out the cost of the basically your memory is saved, that is true, but also you have to account for that decoders are also taken into picture, and also they may be slightly slower in speed corresponding to a horizontal microprogram, but that will not be very high because the way intelligently we have actually placed these signals in different clusters. So till now, if we have looked, actually we were discussing how to optimize the microprograms, and in the first part actually we have seen that how you can optimize it based on actually compressing in the length of the control memory width, so that we can encode some signals based on clustering, how we can optimally select which parts has to be encoded and so forth. Now, we are going to see another interesting way of optimizing the microprogram. How? Basically, by compression in this manner. That means, if you have some say 10 different instructions, you can easily have 10 different microprograms and load them and execute accordingly. But you might have observed that in most of the cases, or in fact in almost all the cases basically, the fetch part is same. So, and for example, if you have an instruction called sub and you have an instruction called add, maybe add R1, R2 and subtract R1, R2. So, you can feel that most of the micro instructions and the signals to be generated will be same, except in only one case. Then in case of add, the arithmetic logic unit has to be configured to add, and in case of subtraction it has to be configured into SUB mode. So, only one bit will be changed or one control signal will be changed, all others will remain similar. So, if you have two different microprograms for these two macro instructions, in fact that will be wastage in the amount of memory space which will be required in the microprogram control memory. So, how can we optimize that? So, basically we can optimize by actually having a single microprogram for most of the common instructions and then diverging out for the different parts and again coming back from where we can start. For example, if we had a single program called add R1, R2 and maybe subtract R1, R2. So, most of the fetch etc. loading from R1 to R2, saving the value of R1 plus R2 or R1 minus R2 to R1 will be similar. Only in one case basically you will find out that you have to make add signal equal to 1 and in this case you have to make subtract signal equal to 1. So, maybe only one line of instruction will be or only one memory word will be different for the two different macro instructions and all other will be similar. So, what we can do, we can write a common microprogram, the fetch part will be similar, maybe all other, maybe some register loading will be similar. Just after that there will be one signal which one will correspond to add equal to 1, another branch will be for subtract equal to 1 and again after executing then you can again come back here, which will lead to storing the value of the ALU to register R1, that is the destination. So, therefore, the second way of optimization is writing same microprogram for different macro instructions which is of similar type and then moving here and there using branch instructions based on the difference of the control signal that is required for that macro instruction. So, in a very broad sense you have some different macro instructions, club them together, write a single microprogram and then depending on the exact macroprogram being executed, which will be told to you by basically the instruction decoder, that is from the instruction register, and the instruction decoder will tell you exactly which is the macro instruction being executed like add or sub. Based on that you jump to the location which corresponds to the independent or the different part of micro instructions corresponding to that macro instruction. Execute the different part and again come back and execute the common part. So, basically that is another way of optimizing the microprogram memory which we are now going to discuss basically. So, whatever I told you basically is given in this slide. It says that we can implement different instruction by different microprogram, but that will be very unoptimized. So, basically this is a simple solution, but will increase the number of memory, because we know that there are so many different addressing modes, so many different type of basically macro instruction and so forth. So, basically what we can do is that we can actually write a micro routines which can be shared. For example, as I told you, like add and sub. So, most of the case will be similar excepting one bit position or the one control signal for corresponding to add or subtract of the ALU. So, you can try to do basically write a single microprogram for similar type of basically macro instructions which are common in type. This slide actually these two slides basically tells you what I have discussed. So, you can read it in offline. Now, let us again. Now, actually I will tell you two things. Two things are very important over here. So, as I told you in the last class that in this unit we will also see how a complete macro instruction is executed in terms of micro instructions, because in the last unit we just saw that how to do a fetch. Here we will see how a total instruction is executed. Secondly, as I told you, we also give some idea that how micro instructions can be micro instructions corresponding to different type of similar macro instructions can be clubbed. Like for example, we are going to show you how a complete macro instruction is executed in terms of micro instruction, and we are going to take the help of jump on 0 M. That is the example of the macro instruction we are going to take, and we will try to see how it is implemented in terms of micro instructions. But again, as I told you, we can optimize based on a single micro routine for different similar type of macro routines, macro instructions basically. So let us take another maybe jump on carry, and maybe you and we say that to jump on M, another instruction which is very macro instruction which is very similar. So this is jump on 0, and basically this is on jump on carry to memory location M. So basically they are very two similar macro instructions. They will have almost similar format and similar type of control signals will be generated, except in the case, in one case you are going to check the 0 flag, and in the other case you are going to check the carry flag. That will be the only difference here. So we will see how to try to optimize and do this. Again, there is another very important thing you have to note over here. If I say that I will have a similar microprogram for different type of macro instructions which are common in type, and then you will, based on the different part you have to implement, you will jump from the main microprogram and again come and execute the different part, and then again come back and execute the common routine. So that means there will be so many branching to and forth in the microprogram. So this type of branching will be actually called the implicit jumps you have to do, because you are writing a common microprogram for different macro programs. So this is not a requirement of the macro program. So for example, if I have add R1 and R2. So if this instruction is there, you do not require to explicitly write jump instructions in the micro routine, because this is not a jump instruction. But as I told you, we will not have a single microprogram for add and sub and maybe multiply. We will have a single routine, and based on whether it is a add, sub or multiply, you will jump. So this is actually the implicit jump routines which will be there in the microprogram. And there is another type of jumps which will be there, which are actually explicitly mentioned in the macro instruction corresponding to that. Like for example, JMP-Z. So it says that if the 0 flag is set, you jump to memory location M. That is an explicit jump instruction which has to be inbuilt in the micro routine. So there are basically two parts. One is called the explicit. That will be because of the instruction type. If it is an add sub, this will not be there, and there will be some implicit type which will be coming into the micro routines because you are doing an optimization. So there are two types of things will be required. So therefore I have explicitly chosen this instruction which is called the jump in, so that I can illustrate both type of jumps which has to be there in the micro routine. And let us assume that we are going to write a common routine corresponding to jump on Z to M and jump on carry to M. So this figure if you look at, so this was already we have discussed in the last unit, just a refresh. So these are the control signals to be generated. This is the branch field address. That means if you have to jump to some location, that value will be given over here. That will be loaded to the microprogram control unit if and only if the load value is 1. If the load value is 1, it will take the value of the branch control address, and if it is 0, then basically it is going to just increment the value. Already we have seen. And therefore, who selects whether we have to jump or whether we have to load the branch address field or just increment, depending on the control select. For example, if your condition select is 1 1, the last bit of 0 will go and you will always be in incrementing mode. If you give 0 0, that is again unconditional jump. If the condition select is 0 0, then basically what happens? The 1 is going, the first line of the marks will be connected, which is 1. So this will be a 1, and always it will be load the value from the branch address and you will make a unconditional jump. The other two things basically are connected to different conditions like 0 flag, instruction register output and so forth. So accordingly we have already seen this thing, and accordingly we will fill up the values. Means these two basically pins in this case can be reprogrammed based on connectivity. And this is the example of a single bus architecture. We have discussed this so many times, just have a look at it, because we will be discussing our example for jump on Z on M on this bus architecture. Okay, I have again come to that. So again recollecting some 2-3 lectures back. So what is jump on 0 does? So basically if you look at it, first with the program counter will be output, that will be going to the memory address. That means whichever instruction you have to read, that address is in MAIR in, memory is in read mode. Select is 0, that means you are going to take default value of incrementing the PC. So select equal to 0. ALU is in add mode, which will do PC equal to PC plus constant, which will be going to the temporary register Z in. Next is you have to Z out to PC in, that means PC will be equal to PC plus constant, and basically and it will go to PC, and also you are waiting basically to still for the memory to give the read signal. So these things are very common, just already we have discussed so many times, just I am giving out the values, I mean just I am repeating it for ease of readability. Then we are saying that the memory data register. After it has read, we will go to instruction register. Now the instruction register has the value of jump on Z to M. Now look at this, this instruction is very important here. It is actually the explicit jump command in this program, in this macro program. So this is the micro instructions or microcontrol signals for this macro instructions. It says that offset field of IR out. Already we have told you that already we have discussed some lectures back that offset field of IR you add it with the value of program counter, and therefore what you get basically that the PC is also stored in Y in for that reason. So Y in, that is the present value of PC plus the offset, if you add it, you are going to get the value of the jump, which will be actually stored in Z. So now by this instruction, offset value of IR, select, add. So one input of the basically of the ALU is basically going to be Y in, and the second value is going to be the offset value. You add it, and Z, actually Z which is connected to the output of the ALU, you have to just recollect some 3-4 lectures back. So Z in actually is going to have the value of memory location M. So that is a repetition. So till now what happens, if you execute up to 4, Z is going to have the value of memory location M. Now it says that if it is jump on 0, if it is 0, then basically you have to load the value of PC equal to M, otherwise you do not have to do that. So what you have to execute the next macro instruction. Okay, so what we will do, basically if 0 flag is set, if the 0 flag is set, then you are going to execute this one, Z out equal to PC in. Otherwise basically you have to go to number 6 micro instruction, which corresponds to N. Now again what is happening, maybe after jump on Z M, because the 0 flag is not set, that means the 0 flag is not set, in that case you have to jump to N. After N what happens, this micro routine ends, and maybe after this macro program, this macro instruction after jump on Z, maybe say add R1M is there in your macro routine. So therefore again the microprogram corresponding to this will load, or basically what is going to happen is the microprogram program counter will start pointing to the micro instructions corresponding to this. That means the next macro instruction will be executed if the 0 flag is not set. So if the 0 flag is not set, you are going to jump over here. So it says that if the 0 flag is not set, then go to end. Basically that means basically you have to load the value of PC with a MPC with the value of 6. Else you do not have to do anything. If the 0 flag is set, that means it is a jump on 0, you do not have to do anything, you have to go to instruction number 5, micro instruction number 5, Z out will be loaded to PC in, and basically you have, and after that you will go to 6, that means after, at present the value of PC equal to Z out, that is equal to M, memory location M. So in the macro program basically we will jump from this to memory location M, which is maybe the instruction which you want to execute, which may be say mul R1 and R2. And maybe just after this maybe we have some called add R1 and R2. So what is going to happen? So if the 0 flag is not set, then you go to N. That means I will jump from directly to 6 basically, and this is the micro program, and the corresponding macro program, what is going to happen is that you will end the micro program for jump on 0, and default the MPC will start pointing to the next instruction basically, which is nothing but add 1 and R2, that corresponding micro program will start executing. And if the 0 flag is set, basically if you see, then the micro program will not jump, it will go to 5, and in that case what is going to happen, Z out will be equal to PC in the macro level, multiple R1 and R2 which is in the memory location M is going to be loaded, and after this micro program will end, and the next micro program PC will start pointing to this instruction micro program and not to add R1 and R2. So this is what is the basic flow. So now let us see how actually it happens in terms of micro program. So if you look at the first micro instruction, PC out, MAR in, read and all these things. So PC out is 1, MAR 1, read 1, and basically add and RN is equal to 1. Corresponding signals are all 1. 2 also if you look at it, Z out, Y in, Z out, PC in, and so forth. 3 is basically if you see MDR out and this one. So it's very simple, you can just trace out the field and you can find out the corresponding signals are 1. So this is very simple, nothing much to look at the control memory here. What is very important is what we have to see in this slide. So basically if you see, this is your condition select and this is your branch address select. Now I will have to do some connection in the figure, which I am going to do. So in this case, this don't care I remove over here, and here I have to put instruction register output, because the instruction register is now going to tell you in this case whether it is a jump on 0 instruction or maybe it is telling a jump on carry. Because I am just assuming that I have written a single macro code, micro routine for jump on Z and jump on carry. So, basically in this case I assume that because if it is jump on 0, so basically I assume that the same micro routine has to be executed, and if the instruction register says that it is jump on carry, then I may have to jump to some other memory location, microprogram memory location, maybe 12, which actually exactly contains the value. For example, as I told you, up to 3 is nothing but it is your basically fetching the instruction, and this is corresponding to the execution of jump on set. Maybe from here actually after if the instruction is jump on 0, from 3 I have to go to 4, 5 and 6. But assume that if this instruction or the macro instruction is not jump on Z, maybe it is on jump on carry to M, maybe it starts from memory location number 12, micro instruction memory number 12, then it has to jump and execute the corresponding instruction from 12. So, this is actually the implicit jump. So, the micro routine will come up to here, after that it will look at the instruction register decoder output. So, if it says that basically it corresponds to jump on Z, there will be no jump, but if it corresponds to jump on carry, it will jump to 12. So, basically what I will do, I will actually connect instruction register to this, the third line of the max, and I will say that if jump on 0 is there, basically it is going to give you 0, the instruction decoder, and if it is a jump on carry macro instruction, it will give us a 1. So, and the condition select at that time is obviously equal to 1 0. So, at this point after a third micro instruction, when the fetch is over, I will give condition select equal to 1 0, and of course branch address select will be 12. So, it will be 1 1 0 0. I assume that from 12 the jump PC, jump on carry micro instruction microprogram starts. So, at third micro instruction of this common routine which corresponds to jump on carry and jump on Z, the fetch is over, which is common for everything. At third instruction it will check the condition select 1 0, that means it is going to check the IR line, which is the third line, and branch address I have kept it as 1 1 0. So, it is checking that if it is jump on 0, so it will just increment. So, from third it will go to fourth memory location of the microprogram, which will be corresponding to jump on Z. But if the macro program, that is the instruction decoder, tells that the jump on carry is a jump on carry, it will make this line as 1. So, if it is making this line as 1, it is going to load, and it is going to load the address of 1100. That means it will microprogram corresponding to jump on carry is going to execute. So, like that. It is a simple thing that is going to happen over here. And here I am connecting the 0 flag output that is going to check. So, this again I am repeating, that is the implicit jump instruction that has to give in because of two macro programs or two macro instructions are clubbed together, that is jump on 0, which basically starts from 4, and assuming that jump on carry starts from 12. So, that is how it has to be settled. So, I am just going to look at again. So, up to 3, as I told you, is fetch, which corresponds, which is very similar to even jump on carry in. So, that will be similar. So, therefore, I do not require to check anything and the condition select. So, I have made both of them 1 1. So, 1 1 means, as you can see, so if I make 1 1 means the last bit is selected, which is 0. If the condition select is 0 0, then max output is 0. So, it is always basically in a increment mode. So, it will keep on incrementing. So, again it will start coming at here. So, here it is very very important. So, here the condition select, as I told you, is 1 0. So, 1 0 means, as I have already shown you, so 1 0 means you are connecting to the third line. Here I have connected the IR output, the instruction decoder output, which actually happens in this way, that it gives 0 and 1, because here we are making a simple assumption, but because we are having two microprograms common. But of course, if you have large number of microprograms clubbed together, then the marks will also be not be a 2:4 multiplexer, it will be a larger size of marks, because corresponding to the instruction decoder output, the number of inputs for the marks will rise, because in fact there are two constants, one is 1 and one is 0, one is for default load and one is for default increment, but the other inputs will be corresponding to different conditions basically. So, here we have just assumed that the two instructions are there, so we have taken a 4:2 multiplexer, but in fact if the number of instructions which are combined and number of IO signals are large, so generally in a practical sense this marks is quite large in size, and the condition select also is larger in width basically. So, for the time being I am just making a simple assumption for you. So, if it is a jump on 0, the instruction register will give 0 to this, and otherwise the instruction register will give 1 for this. So, if it is a 1 basically, if this is a 1, if this is a 1 as you can see, so if this is a 1, it will correspond to basically load, which is nothing but memory location number 12, microprogram memory location number 12, which corresponds to jump on carry. And if it is jump on Z, you are going to get a 0 over here, which will load the next value. So, if you look at it, so it is saying that the condition select is 1 0. That means you are going to check IR output, IR decoder output. And if it is a 0, that means you are actually talking of this jump on 0, so you have to just increment from 3 to 4. But if it is a jump on carry, then from 3 you will jump to another location, which is memory location number 12. I am giving assuming that basically 1 2 3 4 5 6 is common, sorry 1 2 3 is common for both, because 1 2 3 actually corresponds to jump on Z and jump on carry. But 4 5 6 is very much explicit, or in fact you can say 4 and 5 is very much explicit basically for jump on Z, and maybe 11, 12 and 13 memory location will be fixed for jump on. In fact, I should say that not even that, only this one, only this instruction, that is offset IR select 1 if 0 flag is not set, only that part actually is different from for jump on carry and jump on Z. In fact, here you are going to check the 0 flag, and the other case maybe you have to just check the carry flag. So, that is the only different part. So, maybe memory location number 12 is the only part which is going to be different. So, if the instruction register is actually giving the value of 1, which corresponds to jump on carry, so in this case it will jump to this memory location, because the condition is 1 0. So, it is going to check. If it is 1 0, that means the third row of the multiplexer is selected, and if it is a jump on carry, the instruction register value will be 1, and it will jump from this to memory location number 12. So, in the 12 we will have just this instruction, which is number 4 over here, which is only difference between jump on carry and jump on 0. So, that will be executed, and after that you will again jump back and come over here, because after that it is very similar. Again you have to do Z out, PC in and in. So, only one bit will be different in this case, or only one memory word will be different, which is the only difference between these two microprograms, that is jump on Z and jump on carry. That different will be executed at 12, and again you have to come back. So, there will be two implicit jumps. So, one jump will be jump from 3 to 12 depending on the type of macro instruction you are considering at the time, and after executing 12 you are going to have a basically unconditional jump which will bring you back to 15. So, basically this is the implicit jump instruction which you have to put in, because you are adding two microprograms corresponding to two macro instructions. So, I have shown you up to 6 here, maybe you can put dot dot dot, memory location 12 will also have similar thing, which will again correspond to basically the fourth instruction, which is the difference. Now, interesting. Now, basically till now we have discussed basically the implicit part of it. Now, this macro routine or the micro routine for this macro instruction is also a jump instruction. So, what it says that if the 0 flag is not set, then actually you have to go to n, and if the 0 flag is set, you have to just go and increment it, because Z out PC in basically is going to load the program counter with the macro instruction which is located in memory location n. So, this is actually nothing but a basically the jump which has to be explicitly taken in this micro instruction. So, this is the explicit jump the micro routine should have corresponding to this macro instruction. So, of course, again at 4 also there will be a condition check, but all other you can see I have put it 1. So, they do not correspond to any kind of a jump, they just correspond to increment. But here again 0 1. So, you should remember that 0 0 and 1 1 they correspond to default load, and they correspond to jump or not jump basically. But all other combinations basically like 0 1 and 1 0 in this case, they correspond to check of the basically condition, and they will depend and they will lead to jump of some address which is present over in the branch address. So, these two are very important over here, because 1 1 corresponds to basically a 0 in the marks which correspond to just a default increment, and basically 0 0 corresponds to default unconditional jump. We have already seen in this figure basically, again just revisiting. So, 0 0 means this 1 which actually corresponds to load, that is default jump, and 1 1 in the condition actually which corresponds to the fourth line of the marks which is 0 corresponds to simple increment. But all other combinations, in this case 0 1 and 1 0, they corresponds to branch. Now, this is your implicit branch, And the last one, the third, fourth instruction, that is 0, 1, which corresponds to the second line of the marks. Basically, let me erase it. The second line of the marks. Now your answer is basically 0, 1. Now the condition select in this case is 0, 1. So 0, 1 is basically connected to, that means this line is connected to here. So what it says, it is jump on 0 to some memory location. This is say 4th location, this is 5th location, and this is 6th location. So 5th location actually loads the value of PC in, will be connected to the memory location M. That is what is going to happen in PC, and 6th location is N. We have already seen in that program. So that is in the 4th instruction, you are going to check the 0 flag output. That is, for that you are making the condition select as 0, 1. And if the 0 flag is set, if the 0 flag is set, in that case you have to basically jump. That means in the macro program. That means you have to load instruction number 5. But if the 0 flag is not set, in that case you have to directly jump to N, because in that case what is going to happen, this thing will not happen and the next program in the macro routine will execute. So that means what? If 0 flag is not set, that means if the 0 flag is not set, let us look at the routine once again. So if the 0 flag is not set, then you are going to jump to N. That means what? That means there will be a jump if the 0 flag is not set. So in this case, what it says, we have to go, if the 0 flag is not set, then you have to have a jump. So in fact, that is why you have to make it a 0 black flag output bar. That is, the 0 flag output inversion will have to be connected over here. Because again, let us look at this example slightly in a more elaborate manner. So what I have done, I have here the condition select is 0, 1 in this case, which is an explicit condition select. Let us write something, assume something here. Jump on Z is M, okay, and this M location may be having called add R1 and R2. And the next, it is the macro program, and here you may have mul R1 and R2. So what it is saying, if it is jump on 0, remember in the macro program, this is the macro program, this is the macro program. If it is jump on 0, that is the 0 flag is set, then basically you have to load the program counter corresponding to this. And if the 0 flag is not set, just the program counter will be incrementing. That is at the macro program level. Now we see what happens in the micro program level. In the micro program level, we make the condition select as 0, 1. Because we are going to talk about the 0 flag which is connected to the second bit of the marks, and here we are connecting 0 flag output bar. Now why bar, that will be made clear. So that means if the 0 flag is set, so you are going to get the answer as a 0 over here, because if the 0 flag is set, inversion means it's a 0 flag is, you will get a 0 over here. So if the 0 flag is set over here, then what you are going to do, if the 0 flag is set, then you are going to get 0, which is going to be here and which is going to increment at the microprogram level. So in the microprogram level, if you look at it, so that means what, just remember, if the 0 flag is set, if 0 flag set, that means I am connecting 0 flag bar here, so you are going to get a 0 over here and it is just going to increment. This is at the microprogram level. So just see over here. So what happens, if the 0 flag is set, so if the 0 flag is set, you are going to get a 0 in the microprogram control, it is just going to increment. So you are just going to go to memory location number 5. So which says that Z out equal to PC in. That means the program counter value will now have the value of Z, which means in the macro program level, basically the program counter is now pointing to M. Now if the 0 flag is not set, that is 0 flag is 0, that the value of 0 flag is now basically equal to 0. So if this is the case, then you are going to have a 1 over here. If you have a 1 over here, it is the condition select check, it will be load, and the load value here I have put 0, 1, 1, 0, that is 6 in the microprogram level. That means if the 0 flag is not set, that means in that case he is going to jump, and where you are going to jump, you are going to jump at memory location number 1, 1, 0, 1, 1, 0, that is 6, that the microprogram level will now come to 6, which is actually N. So if it is N, you observe at the macro program level, the PC is not updated. So if the PC is not updated, basically what happens, you are going to go from jump on 0 to mul. So in that case, in the macro program level, the jump has not happened. Slightly tricky. Whenever it's a jump in a macro program level, that is here, the microprogram does not jump. Basically it just basically what happens when the when the macro program jumps, basically in the micro program you go from 4 to 5, which loads the PC with the new value. And if the microprogram jumps, that is it comes from here to 6, that is n, you are not actually updating the value of PC, in that case the macro program does not jump. So slightly actually tricky. Once you look at it carefully, it will you can understand what basically is happening. Slightly tricky means slightly the program has been written in a turned about way, that is when the macro program has to explicitly jump, the micro program is not jumping, and when the micro program is jumping, basically the macro program is not jumping. Anyway, that you can look at it, but just look at the philosophy, that is very important. So what happens in the fourth routine in the fourth case, which is corresponding to the explicit jump, which has to do because of the macro instruction, that is the macro program, the jump we are looking at it. So this instruction was the implicit jump because of the common microprograms corresponding to different macro instructions. That was happening because of optimization, but in this case this is happening because of basically this is explicitly required. The fourth jump is mandatory. Without this your program will not run correctly, but the jump at the third location actually corresponds to optimization. So what happened in fourth, again I am repeating because this is slightly tricky, we are giving 0 1, that means you are checking the code corresponding to the second line of the marks. The second line of the marks is connected to we are connecting it to output of the 0 flag bar. So if the 0 flag is there, 0 flag bar we are connecting over here. There. And in fact what happens if the 0 flag is not set, that means ZF bar is going to be 1. That means in this case you have to load the address, that means there is a jump in the micro instruction program. So in this case where the jump will go to 6, that is going to be n. And in that case what happens in the macro program? In the micro program there is a jump, but in the macro program what happens basically? This updating is not reflected over there, so the macro program will not jump, it will just execute the next instruction. But if the 0 flag is set, so we are connecting 0 flag bar there, so if the 0 flag is set, you are going to get the 0 in the marks output. So 0 in the marks output means there will be no jump in the micro program, that is it will not jump to 6, but you will just increment and go to 5. So in go to 5 what happens, Z out is PC in, so in this micro instruction basically loads the program counter, that is the macro program counter with the new PC value, that which is actually offset plus y in, and actually it corresponds to jump in the macro program. So this is the PC is being updated, so it will jump, and basically it corresponds to jump to the memory address instruction which M stores. So there will be jump in the macro level, and after that the micro routine will end, and then what happens basically, the next MPC, that is microprogram program counter, in case there is a jump in the macro routine, it will correspond to basically this part. So if there is a jump in the macro instruction, macro routine, so the MPC will correspond to basically the microprogram corresponding to add, and in fact if basically there is if the 0 flag is not set basically, so in this case this macro instruction will execute, so the MPC will start pointing to basically the micro routine corresponding to MUL R1 R2. But if you think about optimization, so we will have a single micro routine for both mul and add, and in fact the diversification will happen only when you come to instruction number 4, which will tell whether it is a mul or an add. But in fact this actually shows you how basically a total routine executes for a given macro instruction like jump, and also we have explicitly shown that there can also be jumps based on if you have a single micro routine for similar type of instructions. Like here we had a single routine for jump on 0 and jump on carry. We are assuming that the different instruction is placed in memory location number 12, which corresponds to jump on carry. So if this is the case, there will be an implicit jump from memory location 3 to 12, and again it will come back to routine number location number 5, and it will execute 5 and 6, which is common to both. This is an implicit one, and this is there for optimization. But the other one is explicit, it has to be there for the correct operation of this macro instruction jump on M. In that case what happens, you use the 0 1 condition which checks the output 0 flag bar. So if the flag is set, you basically if the 0th flag is set, then what happens basically, you directly execute this one. So if the 0 flag is set, you execute this, which loads the new value of updated value of PC plus offset, that is your M into PC, and in the macro routine there is a jump. Otherwise you directly come to N, and there is basically no jump in the macro routine. So this is how it happens basically. So, you can see this one implicit, this one explicit, and this is the address you have to jump in this case if it is true, otherwise it is similar. So, this one just you have to, I am erasing out, you have to just look at it in your easy pace and you have to try to solve it, then you can easily find out what happens. So, slightly roundabout, just you have to check. So, and then you can see the other two parts at from 5 and 6, basically there is no jump and there is nothing difference in between this micro routine. These two routines are similar for the two macro instructions you are considering. So, there is no requirement of any kind of jumps over here. So, you can see that I have put 1 1 or in end is 6 is end. So, no, there is no question. So, I put XX or you can even put 1 1. So, basically there is no any kind of jump for that. So, it will be single smooth increment of the microprogram counter, it will smooth through, and that is basically going to happen. So, this is very, very important. So, just go through this example in a very nice and a very slow manner, write down yourself on your notebook and see how it executes, and all things will be clear to you. So, only again just repeating, only one thing you have to keep in mind, the third one is for your implicit jump, fourth one is for explicit jump, and we are assuming that from memory location number 12, the jump on carry instruction, the explicit different micro instruction involving that will be placed over there. So, there will be a, in case there will be a jump from 12 and again it will come back to 5, because 1, 2, 3, 5 and 6 are common for both. And in the last one, this is an explicit jump which is jump corresponding to jump on 0. And again slightly tricky, because when there is a jump from here to here, there is no jump in the macro instruction, macro program. But when there is no jump in the micro routine from 4 to 5, there is a jump corresponding to the macro routine. Slightly tricky, you solve it and you are going to understand. So, in a nutshell, what we have seen in this? We have seen that how microprograms can be optimized. One is by compressing by encoding and compressing the control bits, and one way by actually merging most of the common macro instructions, the microprograms are merged. So, if you merge it, there will be lots of jumps here and there implicitly required, because the common parts will be written only once, and for the different part of the different macro instructions you have to jump here and there and come back. And also there will be some explicit jump instructions like jump on Z, jump on carry, etc., for which there will be explicit jumps. So, in that case obviously the micro routine for jump instruction will carry out those explicit jumps. And this is an example by which I have shown how a complete micro routine is executed for a macro instruction, and also how if there are two macro instructions for which there is a single micro routine, how implicitly they will be handled. So, this is a slightly complicated example which actually involves both the type of jumps in a single micro routine. Okay, so, before we come to this unit, let us see some one or two small questions which will see that how we have made the objectives. So, we said that to reduce the control word, we generally do some encoding of the control signal. Mention the factors we need to do the encoding, that is clustering, etc. Explain the encoding techniques in a particular CPU organization, single bus architecture and its control signals. So, basically it will easily satisfy this objective. Estimate the size of control store to implement the control unit. Demonstrate the impact of performance of control unit depending on the format of control word. So, these two objectives will be satisfied once you are able to solve this problem. In fact, you should be able to do it because we have taken explicit examples to show how it can be optimized both at this level as well as this level. This question number 1 mainly tries to optimize the word sizes based on encoding. So, you will be able to do so because we have given some practical example and you will be able to satisfy these two. If different microroutines are used for each different instruction, then the overall would be very large. How this can be addressed? That is by merging at this level. Thus, this also we have explicitly addressed, and I have given you a simple example, although not very elaborately explained, that I have taken one jump on 0 and jump on carry. Similarly, you can take very similar instructions like add, sub, multiply and try to write a common microroutine for that and then see how it basically optimizes. So, in that case, you are going to also have to basically satisfy this objective because there will be lot of implicit jumps because of this merging of large number of microroutines for different macro instructions. So, not only will satisfy this, also will satisfy this objective because you have to know about basically the branch control. And finally, I have asked you to write a microprogram control for execute the instruction add R1M. So, of course, this one will basically requires this two objectives because I would request you to write this add add R1 M and try to optimize the signals in the horizontal level, and also try to add another instruction like subtract R1 M and try to optimize at this level, and then try to see the impact of both how many branches you require and also how many you save in both this direction, both the horizontal level as well as vertical level. Horizontal means you reduce the word memory microprogram control memory word size, and in this case you reduce the number of instructions by merging the common micro routines for different macro instructions, right. So, with this we come to end of this unit, and the next unit basically we will be trying to focus, we will just give you an idea of the whole different units or different lectures we have done in this module. We basically have given an undertaking or assume that everything is a single bus architecture. Next unit will be dedicated, we will try to show how things change if there are more number of buses, 3 buses, 4 buses or a multi-bus architecture. So, next one will not deal in details that how your microprogram will change, how your finite state machine based implementation will change if there are multiple buses. You will be able to do it, that will be very simple once we complete the discussion on the multi-bus architecture. So, in multi-bus architectures you will find out how this microcontrol signals will change, what are the difference if you are having a 2 bus and a 3 bus architecture, 1 bus and a 3 bus architecture, and accordingly you will be able to adapt those concepts to develop microprogram control routine as well as your hardware, that is finite state machine based program. So, next unit will be dedicated on looking at how things are going to change if you are having a multi-bus architecture. Those simple idea will enable you to take whatever we have learned till now from single bus architecture to a multi-bus architecture. Thank you.